Okay, so before you even start this problem, the one thing you need to notice about this triangle over this triangle ABC, what's special about that triangle? It's hard to see this little marking right here, but it's there. What do those little marks mean? All three sides are equal, so it's equilateral. What does that mean for these three angles? They're all the same and they're all 60 degrees. They have to be the same because their opposite sides are the same. And since the triangle adds up to 180 degrees, they must each be 60. Now that we know that, we are told here CD, which is this piece, equals DB, which is this piece. Which means that this line here that goes from A to D is a median. It cuts that opposite side in half. Now, we talked about this with isosceles triangles yesterday. Well, in an isosceles triangle, these two sides are equal. And the third one's different. Here it's an equilateral triangle. Did that change anything? No. Don't really need DF. No, these two sides are still equal, so it doesn't matter. An equilateral triangle will do all the things an isosceles triangle will and more. In fact, the difference between an equilateral triangle and an isosceles triangle is an isosceles triangle, it only works if I start at the one angle that's between the two equal sides. In equilateral, I can start at any of the angles and all these things would meet. So this being a median, and by a median I mean it cuts this opposite side in half, that means it's also what? It also is a right angle here. Yes, it makes 90-degree angles on both sides, of course. In other words, it's an altitude. So if it's a median, it's also an altitude, and there's one more thing that it does.
What was the difference between median and altitude?
A median, remember, hits the middle of the opposite side. In other words, it cuts the opposite side into two equal pieces. An altitude hits the opposite side at a right angle. The third thing that line has to do then has to do with the angle up here. What do I know about this angle and this angle? They are the same. That makes it what we call an angle bisector. Cuts the angle in half. So now looking at what we were asked to do over here, angle CAD. Here's CAD. So that's this angle right here. What do we know about that angle? Has to be half of the 60 degrees. It's 30 degrees. Angle ADB. Well, here's ADB. So that's this angle here. We've already drawn that in. That has to be what? 90 degrees. DCA. Well, this one we just figured out before without knowing the median. What's that angle have to be here? 60. We already had that one figured out. What do you think? I know with my eye bothering me yesterday, I wasn't doing the greatest job of explaining things, so I figured I wanted to go over those three terms again. And like I said, since this is equilateral, oh, sure. Since this is equilateral, it doesn't matter what angle we start from. Get what you needed?
Yep.
So I could go from, as long as this is equilateral like this, I could go from any angle. I could go from this angle here. Let's say I tell you that this cuts that angle in half like that. Well, if I told you that, then you would know that these two pieces have to be equal. And you would know that these are right angles. It's an altitude. So being an equilateral triangle, it doesn't matter which angle we go from. This one here being isosceles, what do we know about the angles? We know these two have to be equal. This one will be different. So if I were to tell you that this angle here, oh, let's say I tell you that it's 30 degrees. It's a little small for 30 degrees. But what do I know about those then? They're each 75. How did we get 75? Yeah, we took 180 minus 30 is 150. Then we divide it by 2. Perfect. So 75 degrees each. Since this is isosceles, the only angle that this stuff here will work on is the angle between the two equal sides. So I have to go from this angle. So if I go from this angle to the opposite side, if I tell you that that's a right angle, that means it's an altitude. Well, then that's also telling me that it cuts this side in half, so those two pieces are equal, and that this part of the angle and this part of the angle are equal. What's that? Yeah. So it does all three, but only if the two sides that are making that angle are the same. So either it has to be an isosceles triangle or an equilateral triangle. See, there's a question on page 297 in your packet, problem number 8. See if I can draw this out halfway is decent here.
You got a little pep in your step today. Good now, huh?
Feeling a little bit better.
Good.
Okay, I gotta move this one just a little bit here, make this work. There, that looks better. So what are we getting for information? We are being told, looks like it's 125 millimeters, is what we're looking at here.
Yeah. Which problem is it again?
Number 8 on page 297. $260 center to center on the holes. $125 here again. And 300 total. That's bad notation there, but that works. 360 here. We're asked to find B. So what we're finding here, what this is telling us, if the distance between these two holes is 125, and the distance here is 125, what that's indicating to us is that these two lines are parallel. If we measure them at two different points and they're the same distance apart at two different points, then they have to be parallel. Remember, we talked about a lot of people define parallel as being two lines that never intersect, but the technical definition is they're always the same distance apart. So because they're 125 millimeters apart here and over here, that makes them parallel. And if those are parallel, that means this big triangle and this little triangle are similar. So because of that, then, which piece are we trying to find? We're going to try to find A here. Well, that A better be the same as this side. It's not giving us any perpendicular, but the way that's marked, it looks like this has to be a right angle. Just by the way it's marked. I mean, it's not drawn that way. It looks like it's less than 90 degrees. But the way everything's labeled, that has to be a right angle. So that's saying is that this...
Which one's right angle?
This one up here? Yep. So that's saying is that this must be a rectangle here. So this side that's marked side A has to be the same as this side here. Yep. Opposite sides of the same rectangle. So that means this here is A. So whatever that side is going to be the same as A. So now what we have is we have A and B here. Do I have any of the sides of that little triangle? Oh yeah, I can. Yeah, this here has to be 175 because 300 minus 125. So now that we have that one side, we know that the 300 on the big triangle has to correspond to the 175 on the little triangle. We'll put A here. That's from the little triangle, so it goes on bottom with the 175. That corresponds to the 260. Because A is over here, so that corresponds to this side. B would correspond to the 360. So now we cross multiply and divide. 175 times 260 divided by 300. Gives us 151.67. Since everything's given to the nearest tenth, I'd probably round that to 151.7 is your answer. Now then for the second part, for B, we still got 300 to 175. B is still from the small triangle, so that's going to go on bottom. And it is the 360 that goes above it, because those correspond. And we'll cross multiply and divide. 175 times 360 divided by 300. Is 210 for B. Any questions?
You still use A squared plus B squared equals C squared to find B?
You could, if you knew for sure that this was a right angle. And I guess the way I said it, not necessarily, you can't necessarily assume that's a right angle, but you have to assume that these two sides are parallel. So maybe I shouldn't have said that you could assume that's a rectangle. I probably should have said you can assume it's a parallelogram. Well, we can double check here. Let's look at the square root of 260 squared plus 300 squared. That does not give us 360, so it's not a right angle. So you can't assume necessarily that's a right angle, but you have to assume that that's a parallelogram. So I shouldn't have said a rectangle. You have to assume it's a parallelogram. But technically, yeah, it should have been indicated that this line and this line are parallel. Otherwise, that problem isn't solvable. So as you can see, the toughest part in these problems isn't doing the math. Once you have the two triangles picked out, and you know that they're similar, it's easy to do the set up the math, the proportion, and solve it. It's finding the triangles and figuring out what those missing sides are. That's the tough part. Any other questions out of the packet that you want me to go over? Okay, so if you're still working on the quiz, that's fine. Please feel free to take as much time as you need. We're going to go ahead and start some of our new material here. Just to let you guys know, we are closing in on ending this unit. This is just our preliminary shapes and vocabulary unit before we actually start the right triangle trig stuff. So probably Monday or Tuesday next week, depending on how the next couple days go, we will be looking at our Unit 3 test for the semester. So just to warn you, that's coming up. So today then, we're going to talk about circles. And most of what we're going to put up here for vocabulary is stuff we've seen before. This next little part is going to be a lot of review. When we're dealing with a circle, there are three main pieces that we're going to look at. Of course, the first one of those is a radius. A circle is often described as being completely defined by its center and its radius. So the location of its center and the distance of its radius actually locates every point on that circle. Now the next piece I'm going to define is not one of the main things, but one of our main things is derived from it, and it's called a chord. A chord is just a line segment that has both of its endpoints on the circle. And the reason I defined that one first is the next one is a form of a chord. A diameter, the technical definition of a diameter is a chord that contains the center of the circle. And of course, we know that there's a relationship between the diameter and the radius. That is just the diameter is 2 times the radius. Third piece I'm going to describe, or third vocabulary term, we've seen the circumference. Circumference, just the distance around the outside of the circle, the perimeter of the circle. And our formula for circumference is what? There's two of them that we have. Not pi r squared, but pi times diameter, or 2 times pi times radius, since the diameter is just 2 times the radius. So those are the main ones that we already know. Other structures that we will become familiar with through trig. One is a tangent. A tangent is a line that just touches the outside edge of a circle, but doesn't actually penetrate the circle. And one of the qualities of a tangent that's going to be very important to us is that a tangent, if you take a radius to that point on the circle where that tangent touches the circle, that's called the point of tangency. A radius to that point of tangency always forms a right angle with our tangent. Now that's very important to us because if we do V-block work and stuff like that, where you have round stock sitting in a V-block, pretend that looks round, well, that means the radius of that circle is going to be forming a right angle with that V-block, the surface of the V-block. Another one looks like this. It actually cuts through the circle. That's called a secant. So the tangent touches the circle but never cuts into it. A secant actually cuts through the circle. A secant, the technical definition of a secant is a line or a line segment that contains points both inside and outside, or both interior and exterior to the circle.
So how do you know if that's a chord or a secant?
Because it continues on. It has to contain points both inside and outside. Chord is completely in. Now we've talked a little bit about this next piece when we did areas and arc lengths and stuff. This, of course, is called, the wedge itself is called a sector, that pi wedge. The blue piece there is called an arc. And back last semester, when we looked at the arc and the sector, we defined those, we found their size based on what's called a central angle. That central angle defined to us what fraction of the circle that sector was. If you recall, if we knew the area of the whole circle, to find the area of the sector, it was the area of the whole circle times theta stood for that central angle over 360. So that told us what fraction of the whole area that sector area was. And the same for the arc length. The arc length was equal to the circumference times that central angle over 360. And then, of course, we have that chord that connects the ends of the two radii of that central angle.
Arc length?
Arc length is AL, yeah.
No, what's the circle?
The blue?
No. Go over in the equation.
Over here? Oh, C?
The O.
The O, that's theta. That's this angle right here. That's the Greek letter theta. Just feel the love in this room today.
Hey, you know what though? Next class, when he needs help with his project, I ain't gonna be there. We're done now. This stuff we got.
Okay, so Greek theta there.
So the top one is the arc sector.
This is the area of the sector. And this is arc length. So then we have this green line across here, that chord going across there that cuts out this little slice on the very edge. Remember what that purple slice is called? That was called a segment. And if you recall, we found the area of that segment by finding the area of the whole sector and subtracting out the area of that triangle. Well, today we're going to define some other angles. That's a central angle.
How do you find the segment?
The segment, you found the area of the whole sector. And then you found the area of the triangle. We subtracted those two. The sector is the difference between the segment was the difference between the sector and the triangle. As we need them, yes. Actually, at this point, we're not going to be actually calculating the areas. We're going to be looking more at the arcs. And not necessarily the physical length of the arc. We're going to be looking more at the arc as a fraction of the circle. This angle here is what we call an inscribed angle. Inscribed means on the circle, in the circle. Like an inscribed polygon is one where all the vertices, all the corners of the polygon are on the circle. Well, here's an inscribed angle. Its vertex is on the circle. And we're going to be looking at the relationship between that inscribed angle and the central angle. And, of course, the arcs as well. We're also going to see something called a tangent angle. If I have a radius of a circle and a tangent, of course, that's going to be a right angle. But I could have, from that point of tangency, I could have a chord. So a chord can form an angle with that tangent. And we're going to be looking at relationships on that. And, of course, there are secant angles.
So an angle is a tangent angle?
Yeah, that's the angle. Well, the tangent angle usually is talking about the angle between a tangent. Oops, come on. A tangent and a radius, like that. But this is a tangent and a chord here that form this angle.
Yeah.
So that's an angle between a tangent and a chord. Here, we have two secants that form an angle. And for a secant angle, we're looking at the angle that is outside the circle like that. And we can also look at an interior angle that's formed by two chords. Obviously, both of those two angles are the same because they're vertical angles as well. And these two angles here are going to be the same because they're vertical angles. So we'll look at how we figure out what those angles are. So let's look at arcs more. Last semester we talked about calculating arc length. If I have my radius here, and let's say that this is an 8-inch radius, let's say I have an 80-degree angle here. The arc length was found by finding the circumference of the circle C is equal to, since I have a radius, I'm going to use 2 times pi times the radius, which is, what, 50.24 inches. If I use 3.14 as pi. That's my circumference. So my arc length is then found by doing what? What do I do to the 50.24 to find my arc length, this piece? 80 over 360. Very good. So 11.16 is my arc length. For this piece, for this unit, though, we're going to look at what if we don't know the length of that radius? Well, we could just call this an 80-degree arc. And as long as we see it as an 80-degree arc, we can figure out its size once we know the radius. But for a generic circle, we can call that an 80-degree arc. Because if I have a single circle here, and I have this 80-degree angle here, there's my 80-degree arc. If I throw in a different angle here, but I know that this is still 80 degrees, what do I know about the length of this arc? It has to be the same. So we know that they're both 80-degree arcs. We know that they're the same length. We just don't know what that length is until I know the radius or the diameter of that circle. But knowing that they're the same is important to us. In fact, not only are these arcs equal like that, but they're also proportional. If I have a 40-degree angle right here, what do I know about this arc? It's a 40-degree arc, but it's also equal to half of the 80-degree arc, or the 80-degree arc divided by 2, because it's half the central angle. So the ratio of the central angles is equal to the ratio of the arc length. This had half the angle, it had half the arc length as the 80-degree angles. Other relationships. Let's say I don't know what the radius of this circle is, but I know that this chord here is 7 inches long. If I have another chord here that's 7 inches long, what do I know about those two arcs? They're the same. If they have equal chords, they're going to have equal arcs that they cut off as well. So we have a bunch of those relationships. Since we're talking about those chords, I want to take now a radius that goes through that chord coming out here. If that radius intersects that chord at a 90-degree angle, at a right angle, if we look here, we've got a radius that can go out to either end of that chord. We know that those two distances have to be the same because a radius is equal to any other radius of the circle. So what we have here, as we were talking about earlier, this is an isosceles triangle. If that's an isosceles triangle, then if this forms a right angle, what else does it have to do? It has to be a median. It has to cut those into equal pieces. And it has to cut this angle in half. It's an angle bisector. So yeah, it's an altitude, a median, and an angle bisector. If it's any one of the three, it's all three of them. So that's something we'll look at more tomorrow. The new packet, and for you guys just came in, there's a quiz you missed earlier, and then I got a new packet I'll give you in just a second here. In the new packet, page 305, we'll just do 1 through 8. We'll come back and talk more about the rest of them later.
Metal, or whatever. After I got pulled over. Yeah, it was great. Got pulled over, sat there with my blinker on for so long. And then actually, when I tried to go home, all of a sudden everything started getting dimmer. Then dimmer, I was like, oh shit, look out.
I don't see the alternator's going bad from sitting there idling, or?
I don't know. I got it checked over at O'Reilly's not more than a week ago, and they said all of it was good. But I don't know. I think maybe, I don't know.
Thanks.
I might. I got tools. I did fucking weird car though. Oh, 2004 Malibu. Yeah, it's weird.
Really good at cursing.
Yeah, me too. Me too. This stupid thing has the transmission fluid, which I know needs to be changed. with why batteries not being charged. It's not a little dryer, and in order to turn the belt, the engine has to turn, and if it's spinning too much and not actually achieving the proper RPM, then the engine isn't turning enough.
One mechanic told me to change my transmission fluid that needs to be changed. I'm thinking like 3 more to this day. It's not, sometimes it's not doing because it's cause problems.
Once you get over so many miles, there's crap that's in there that when you change the fluid, it can knock it loose.
Yeah, you can actually,
You end up having the transmission rebuild. Talk to the guys.
if you sometimes, my mechanic told me it's not gonna, he doesn't do that. It's not good to do it. That's not good to do it. Some kind of problem. So ask about that around, I don't know the particulars, but that's what he told me because I was gonna get it done. And 2 mechanics that I brought it, yeah. 2 mechanics
But also,
that I brought it to, because it takes out or something and it